In this segment, we're going to explore what's called ortho-para-directing groups. Methyl is one of those. CH3 is an OP director. That means ortho-para-director. And NO2, which is the other group that's on benzene, is a meta-director. I guess you could have called it an M-director. And the reasons will be because of what happens during the mechanism. You can't do this on a test, but I want to skip the generation of the electrophile. You've got to show me that. We did that on a video earlier today. I just don't want to repeat it. We generated the electrophile, and this one generates the electrophile here. Okay. And that's not right. My apologies. There's a Cl in the middle still. There, that's right. You got to give that Mac on a test. All right. So what I'm going to do on the first one is show the mechanism. And we're going to go towards the major and the minor product. So I'm going to have to show it twice. It was ortho and para, as the title implies. And we need NO2 again. And we'll do the para mechanism on the top. Wow, apparently we won't. Para mechanism on the top. And the ortho mechanism down here. And you'll see they both generate a cation that is very nice. This, I'm looking at the one, well, apparently I didn't do it right. Sorry. Of course, the first thing I drew. I was looking at the one right above it. This one I used the pair of electrons to the left. I put the new group on down here. NO2 has an H and a cation. And the thing I really like about this cation, right now it's secondary allylic. Do you agree? Remember how stable that is in theory? Can you give me a new number without any words? How stable it is? No, it doesn't go up by 0.3. For being allylic, it goes up by a whole 1.5 degrees. Your estimate of the stability of this cation is 1.5 degrees higher than the number that I wrote already. Please remember that. Allylic and benzylic, same story, both. So yeah, that's a really nice cation. It gets nicer. With resonance, you can generate this cation. Tertiary allylic. Can you tell me how stable that is? I need a number. 4.5 degrees. That is an exceptionally stable carbocation. So if you can put the group para, one of the resonance forms has an exceptionally stable cation, and that's why you would like to put the group para. Okay? Now doing the ortho mechanism, we see everything we need here. This reacts with this to give the ortho nitro carbocation. Looks like I was doing those in green. No, not yet. So we have the methyl already there. We're putting the nitro on the ortho position. There was already an H here. The cation is already here. I don't have to think about resonance in this example. What did I do? Oh, I didn't do it like I drew the molecule at the top of the screen. My apologies. I do not want to rotate and mess your mind up. Can I redraw this? Please bear with me. I want to put it on this ortho position up here, not the other one. I wanted it to reflect the way I drew the molecule originally. Didn't touch this. Didn't touch this. We had the methyl here. The cation is there, which is already 4.5 degree cation. So tertiary allylic already, you don't need to talk about other resonance forms. Roughly the same stability as 4.5 degrees. Because this cation exists, that means the mechanism should go this way. I want to point out that if you try to put the meta position, you will not get any 4.5 degree stable cation. I will do the hypothetical attempt at the meta mechanism. You would have to use either this pi bond or the one to the left. They both are attached to a meta carbon. Sorry, it's a little sketchy in terms of, it just looks sketchy, that's all. I don't know what to do. Here's the hypothetical meta mechanism. Hypothetical because you won't get any of it. You won't get any of it for reasons I will discuss right now. Meta NO2. Existing H was here. Sorry, cation is here. That's a terrible looking cation. Do all the resonance you can. Does it get to a better cation is the question. Secondary allylic is going to become another secondary allylic. Is that better? No. Resonate some more. Your last resonance form would be, let's see, we didn't use the pi on the left. Do that. Is this more stable? Answer, no. And plus is there. Meta mechanism doesn't give a 3.5 degree cation. meta mechanism doesn't happen for that reason. There you go. So if you have a group that can stabilize carbocations like a methyl, hyperconjugation stabilizes carbocations. If you do not remember the word hyperconjugation, review it now. We're talking about carbocations all chapter. One thing that stabilizes them is hyperconjugation. There's another thing that stabilizes them even better. If you have that group with a lone pair, that can resonate with a cation. Para, major, ortho, minor. Okay, so that's even a stronger, we call it an activating group because it's got a lone pair that can resonate with the carbocation. Only if you do the mechanism in the para or ortho positions. If you do it in the meta, that lone pair cannot help your cation at all. So guess what? You don't get any meta product. Okay? Now, without redoing all the mechanisms, I just want you to use your imagination. I'm only asking you to do one imaginary step. Just make this into an NO2 group in your mind right now, all the way across. NO2, 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 NO2. Okay? NO2 looks like, well, we don't have to go very far. NO2 looks like, where are you, NO2? You have to go back to the start of the day. Where are you? There he is. Look. There's a cation on the nitrogen. Do you want that adjacent to a carbocation ever? So which mechanism never has this is now a nitro in your imagination, right? With a plus charge on the nitrogen. During this mechanism, none of the resonance forms has the cation next to the nitrogen. If you did the other mechanism, where this is a nitro, oh my goodness, you know what you just did? You generated a cation on an atom adjacent to a cation. You're using your imagination again. This is an N plus right here. Do not do that. Okay? So if you have a nitro on your benzene, are you going to make any ortho? Are you going to make any para? No, you don't want to risk having an N plus adjacent to a cation, which is what happens in the ortho and para mechanism. Do not put the next group, ortho or para, when you have a nitro on. This is a meta director. You will only get one result. Your new group must go meta, as we discussed in the previous video. And the new group's a methyl here. To avoid N plus bonded to C plus in the EAS mechanism. That's the main reason meta directors exist. It's not that they're helping, they're actually slowing the whole ball game down because they're cations, and you're making a carbocation intermediate attached to one of your groups that has a cation in it already. This is a very slow reaction to start with. It goes even slower if you try to put the groups ortho or para. Meta by default's a little faster, so it happens. Okay? So there's a table in your textbook that's the most important table of the semester, where it outlines all the directors. You better know which ones are ortho para directors and which ones are meta directors. And look for the things they all have in common with each other, so that it's not just memorizing 15 different groups. If you're memorizing 3 things, it's a lot easier than 15. And what are the 3 things you have to memorize? Alkyl groups stabilized cations by hyperconjugation, they are OP directors. Atoms with lone pairs, like ethers and alcohol and amines. Lone pairs stabilize cations even better by resonance. They are also ortho-para directors. Groups that have an atom attached to benzene, and that atom is either a cation or a delta plus, which is very positive without being a cation. Every one of those, meta director. Why? So you can avoid a carbocation adjacent to that positive atom or the slightly positive atom. And we had a question. Thank you. All right, you said I answered it. It's my favorite question. No, I like other questions. Make the teacher think. Initially, they don't like it because, you know, it's awkward. But when you get into it, that's what makes teaching exciting. Okay, so we got this as another thing. Did you copy all that down? And I'm going to kill it.